building on the work of Leif, 2018, some of them are in this room, and they pose the problem pretty well, which is that if you have well-scoped or well-typed lambda terms, then renaming, substitution, and other kinds of traversing over the term have a common structure. And the question is, how can we abstract away the structure to allow us to cut away the boilerplate as much as we can? And to differentiate what I'm doing from them is that they have this deep embedding using a universe of descriptions, whereas I'm going to be focusing on a shallow embedding, which is more using kind of shallowly embedded fixed endofunctors. And this is more approach that's common in kind of Haskell world, where type level fixed points are more accepted. In the Agda world, people usually prefer to work with strictly positive functors, but everything here is interoperable with that. So here's a plan. First, we're going to just recap fixed points functors. Then we'll look at fixed points in other categories. Then I'll show you free relative monads for syntax, and then kind of algebras for semantics. So first, just to have a quick intro to fixed points of endofunctors, is you have your type mu, which takes a fixed point. It takes some base functor, and it brings it to a value. And you have your type of algebras, FA to A, and you have your catamorphisms. And the nice thing about this is that you can formulate a single catamorphism for arbitrary data types. So since you've seen this probably from JSON, we can define semi-rings, and notice that there's no recursive positions here. It's just a flat type. We tie the recursive knot using fixed we defined earlier, and then an algebra is defined on the non-recursive data type, and we use the catamorphism to lift it to a recursive data. So this is fairly standard. And you might notice here I put a boilerplate. This requires a pointer. These get annoying to write, so standard trick is to use Medler algebras. What they do, they look a bit tricky, but I'll explain why. But essentially, they allow you to remove the functor constraint here.
And Zanzi, sorry, are you able to like collapse the window on the side there? Just people are saying they can't read the text, and I think it's like as well framed as we're going to get it.
You can't read the text.
Just the like window with the marker on the side, or is that able to like close or collapse?
You mean this thing?
Yeah. If you close it, does the preview go away?
It might close, yes.
And for the preview, if you keep the same window as
oh, that's clever. Yes. Yeah. Oh, sorry. Okay. Okay, let me go 1 second first. So here we have our member algebras. Okay, it's a small typo, but the point is that the mental algebra is actually equivalently expressed as algebra over coinata. And coinata, okay, this is the programmer's definition of coinata. Usually mathematicians get a bit confused because the extension is implicit. So I've kind of written out the kind of more familiar form to mathematicians, like this would be a coent. But essentially, this allows us to kind of, it's a free functor in a way. So we have your free semi-ring as a data type, and then we take the free functor over it, and algebras over that are known as non-algebras. Now, if you know your Khan extensions, you'll know that coinata is a form of a Khan extension. So that's a small foreshadowing that we're going to get more Khan extensions. So that was a quick recap, and now we shall look at fixed points in other categories, which some people might know and some might not. So endofunctors. Now our objects are endofunctors type to type. Our morphisms are natural transformations. We have algebras over functors over the category of endofunctors. We have our higher coinata. and we have our catamorphism, and if you notice, the entire setup is the same as what we've seen earlier, it's just the object's morphisms change. A common example of this is monads. We can define a monad, the base function for monads, and we take the fixed point over that, and this gives us free monads. And so essentially, a monad is a monad. Applicatives are also monads in the category of endofunctors with a different tensor. This is day convolution, which again, written in more mathematical form here, but same idea. Now, another example is fixed points over index sets. So same as before, we have as objects index sets or discrete presheaves. We have morphisms between them. Examples of this are predicate transformers. So this takes a predicate K to type to a list of Ks, and this type means that everything inside satisfies the predicate P. Any, same thing as before, but now it's more of an either, an n-ring either, means that one thing in this list satisfies the predicate. Then doubly indexed fixed functors in the sets give us graphs, so they're indexed by source and target. Same setup as before, like I'm only showing the code to emphasize how similar all these definitions are. But here we can say three categories are fixed points of functors, and we can also do type things. So we can say Cartesian categories, we can form them as a endofunctor on these on graphs. And finally, just last example, multigraphs. So these are indexed twice, but the source is indexed by a list of vertices. And the interesting thing about this is that these guys start looking like bindings. So the identity of a multi-category selects an A from a singleton list of A, and composition, it has some list of things gamma and S, and then it has S3 and gamma, and it composes. So this is essentially a lead binding, and this is essentially saying that lead bindings are the same thing as composition in a multi-category. And okay, so the topic of the talk is bindings, and so this gives us a binding, but we had to go a long way here. We have these doubly indexed sets, and if you just want to work with first-order algebras, first algebraic theories, that's a big setup. So the question is there a more elementary theory of binding that we can use? And this brings us to, before we go to that, the question is, all of these definitions could actually be united if we had a little bit of extra things about type theory. So it just won't accept this generic thing because this is not type. I think if we had kinds, we could have formulated everything as just unified these definitions, which I would like. But yeah, so we want a more basic theory of binding, and usually monads are associated with binding. And so I'm going to look at monads, but I'm going to look at them from the function programmer's point of view and the mathematician's point of view, because they're slightly different, and people don't usually emphasize this. So we look here. We have a free monad, similar to what we had before. And usually functional programmers, they care about effects. So if you take your free monad over F, you interpret it in some monadic context F. And so similarly to what we had before, we can actually remove. So the splinter constraint can be removed by using what programmers call freer monads and mathematicians call extension systems. So we replaced join by this bind. And if you look at it, you'll see the similarity to the bind, the Kleisky bind of a monad. So it's like a free monad with a suspended continuation. And this lets us get rid of the functor constraint. And the reason I'm just emphasizing this is that this guy here is coordinate again. That's our kind extension from before. So it's an observation. We can say that middle algebras, they put the coordinate into the algebra and keep the fixed point. But for your monads, they put the kind extension into the syntax and keep the semantics. And the question we're going to look at is what happens if we kind of try and do both. Will we get some extra terminology? So that's the program of monads. Now we should look at the mathematician's monads, and it's the same kind as before. And this interpreter is interdefinable with the one before, so this isn't semantically different. But syntactically, just the way people think about these is that the free monad is now describing syntax trees. So instead of pure values, we think of these as variables, and instead of effector values, we think of this as being substitution. And we have a chiomorphism, and you'll see there's an functor constraint. And the reason that there's an functor constraint is that now it's the algebraically free monad. So the monad action, sorry, there's the monad constraint. The monad action is purely determined by functional algebra. It's just formal substitution. And oh yeah, but the problem here, the reason you don't see that. The reason you don't see this very often is actually representing variables if you're doing this in Haskell becomes a problem because you don't have the blended types. So if A is a string, you couldn't evaluate this into a pure value. You would need maybe or either or some other context to handle the variables. Or you could maybe use a fixed type, finite set, but then your set of variables is fixed, and that's kind of bad. So usually mathematicians, they would prefer to use linear theories here to be a bit more precise about the hierarchy. So linear theory, one representation could look something like this. So we have a signature, it's indexed by a natural number, and you say 0 has 0 things, mult has 2 things. And how would you organize this? Well, wait, oh, slide disappeared. Oh, no. Unfortunately, the slide disappeared, but there was so I think first there's a representation I've seen in Connor's papers, and I think Flex people use them as well, where you take a layer of this, take a layer and take a vector of values, and then the vector holds the context. So this lets you form syntax trees over these guys, but the problem is that a vector of these functors is kind of like this nested type. It's no longer a monad. We don't know what it is. It becomes purely syntactic. And we want to have some nice semantics. Well, it turns out that vectors are representable functors. So vect can be seen as a function from fin n to a. And this gives us this representation of a fin index monad. So takes some variables as before. And here, so this is where the vector went, but now we just have this function. Again, so it takes a layer, takes a generator, and then says what to fill into it. And similar to how before, the freer monad was a suspended bind. This looks like a suspended bind of a relative monad. So this is the free relative monad where J equals fin. And this actually, if you squint a bit and you see the kind of extension here, this is actually the same as the definition of an element. But so we give them algebras. So how do we interpret this? So we give them this guy. It looks a lot similar like a Mendel algebra. If you remove J or set it to identity, you will just get back a Mendel algebra. So kind of algebras generalize it. And we get an evaluator for the syntax trees. So essentially, they get an environment for variables. They get a Khan algebra, this indexed by fin, our free monad, and this stays the same. The actual evaluator is the same as before, which is neat. So, and because the extension systems are called freer monads, I think this freest monad is a bit of a joke. Slight generalization, but essentially, to define a freest monad, you take the left Khan extension, and here it's I extract this in the data type. You can see there's an existential, an arrow from J to B, and a layer. Then we form the freest monad. Now we abstracted fin into J, and here we have 1. And we have algebras, which are the same thing as algebras over left-hand extension of GeoGraph. And our catamorphism now just takes a J-based environment, a algebra, freest monad, gives us a value. And this will mean there. So it's, that's like the freest monads is that they generalize the so-called freer monads a little bit. So yeah, and you can actually, as I mentioned earlier, you can subsume freer monads by just setting J as identity, and then you get back your original evaluator. And this is nice because there's a bit of a debate in functional programming. You know, do we prefer linear theories? Do we prefer free monads? And from the point of view of relative monads, they actually get subsumed. So, and just as an aside, some of the products are very nice in this representation because we already have products. That's just our arity, and we can present some as a list, and we can use Algebras to automatically prove that any generator we use is actually in this list. So you'll have this syntax which almost identical, but now we have a list of generators here. So I think this is for potentially some ideas there for like backends of languages. Like, I mean, programming in this may not necessarily be easy, but I think the idea here is that you could think of this as a semantics for the backend of a language. Like it means that if you don't want to expose your user to unrestricted recursion, and you just want to have the one catamorphism that does the compilation for you, it means that you can now have more data types that you can capture. So, right, and then the question is, what if we do multi-sorted things? Because those were single-sorted.
So one question just for understanding. You just said that both the V theories and monads can subsume by relative monads. But isn't it, I mean, what do you mean by subsumed here? In the sense that, for me, I mean, the V theories already subsume monads. So what do you mean by subsumed?
So okay, good question. Let's just clarify. So let's go back here. So when I say subsume, so Levier theories correspond to binary monads. So there's actually more monads than Levier theories. But so what I mean specifically is that if you vary this functor J, if you set it to identity, then you will get back the evaluator for the free monad, which I guess the free monad has to be finished as well. So they're equivalent. But if you set J equals to fin, you will get an evaluator for Levier theories. So this evaluator gives you both. And actually, I don't go into the talk about it, but for instance, J could be an inclusion of a subcategory of type into type. So for example, types with an OR constraint. And so this would let you do free monad set as a free monad, because set is not a monad in Haskell because it requires the OR constraint. So, right, and these are single sorted, and let's say we want multi-sorted. So the multi-sorted theories, instead of indexing by a natural number, we now have a list of source types and a target type. So just some random operations, addition takes natural to natural, or takes booleans, injecting a value. But the idea is that we're now using a lem index monad. And why it's in a lem is that this continuation here is actually the representation of a heterogeneous list. So the same way that vectors are represented by functions from fin, heterogeneous lists are represented by function from a lem. And this lets us again use a syntax for multi-sorted algebraic theories. Oh, I say algebraic theory, these guys don't have equations because everything is free. But I think this encoding would work really nice with some of the work that people working on Flex are doing. So I'd be interested in talking to people doing Flex about something there. So these are first order, okay? And so far, okay, again, we want to talk about binding, but so far we're only using binding as a meta operation. The actual theories we're doing doesn't have binding in the theory. So if we want to talk about theories that have binding in them, There's some good papers by Marcelo Fiora, which use second-order algebraic fields. So they're kind of, because the higher order, you can talk about pipes, because essentially, okay, on the first side, it's a little bit messy, but essentially you have a list of theories as a source, and you take it to a theory and target. And so, for example, now abstraction has a term with a free variable s, just a t, and we form an abstraction this way. And the application takes two terms. One's a function a to b, one's an element a. So you can think of this having terms together. And so we can clean this up a little bit. Because so at this point, we could try to think, what is the relative monad that captures second-order algebraic theories? You could try and define it directly, but actually, if we clean things up a little bit, we can see that, so I've added these turnstiles. So you can see that we rewrote our first-order theories a little bit, just set this here, turnstile, and then second-order theories, we have first-order turnstile and second-order turnstile. The thing is, from the point of the compiler, it's actually the same. So it's a theory of theories, but these are just for readability for humans. But so as we can see, these are actually, we can abstract away a certain common pattern, and we get this going. So sig over O, so it actually subsumes both first order theories, second order theories, and then we can just go. So thanks to dependent types, turns out higher order algebraic theories are actually in this code. And we have our Can algebra over this guy. Again, it's a little bit tricky to read, but essentially, yeah, they're just doubly indexed functors. So second algebraic theories are pretty cool because they distinguish first order variables from meta variables. And if you're trying to do something like a type check or unifier, when you have both, this kind of gives you like a principled way to do so. However, we haven't actually answered our original question, which is, how do we do this? Like, we can restate it using the technology we have so far, but it doesn't necessarily help us answer this. So what is missing? Well, if we take out the recursive positions from it and make it into a base functor, the question is, can we express renaming and substitution as algebras? And now, just as a show of hands, people pay attention, raise your hand if we can express them as algebras. And raise your hand if we, okay, and raise your hand if we can't. Okay, no one's. Well, the answer, everyone's lost. Well, the answer is the way using what we have so far, we can't, because the types are changing. So it's hard to see in actual implementation because the dependent types are very smart, but essentially as we're traversing the term, there is the types are changing. And normal folds are not enough to capture that. So normal folds will not succeed. However, we do have one more trick up our sleeve, which is counterforce. So it turns out, originally this insight was from a paper by Neil Gunny. They used higher order functors to represent lambda terms. So instead of fn, they use maybe. And they represented the Brownian binders this way. And they found that you need two things to make this work. Is first you need a distributive law of maybe over term, which maybe always has this distributive law. And second, you need to write an extension, which allows you to thread your evaluator in a way that lets the type change. And so, yeah, essentially, you're able to express this type changing follows algebra, which, okay, so we can, it's just we couldn't do it before. We needed this one insight. And the cool thing about this, so distributive laws of maybe are easy to talk about because maybe is an endofunctor. With relative monads, we no longer have endofunctors, we have these index things lying around, but despite that, all of this generalizes. So if we look at well-scoped terms again, we find that we can form the right kind of extension over these index functors. And now we have S here instead of maybe. And we find that, okay, lots of code, so apologize. We find that renaming essentially takes a functor over finite sets to terms and traverses and does renaming. And substitution takes this Kleisli functor. If you squint at this, you'll see that this is the relative version of traverse. If you remove the fins, you actually get back the Haskell traverse back. And so substitution carries this functor through the structure of the term. And we can actually extract the column pattern using what Conrad calls a kit. So essentially, we have a single traversal for both renaming and substitution as we wanted to. And the same pattern applies to a bunch of other algebras, normalization by evaluation, just normal evaluation. So it's quite expressive, this framework. And finally, does it generalize to all type terms? Yes, it does. So now we look at the, again, all type terms of the data functor. We define our right-hand extension. And okay, right behind slide making, but essentially these become functor. This is the renaming function from before, except generalized to LM. And going here, and this is the Kleisli substitution functor. And just as before, we have an algebra that traverses a type term. So yeah, that was the talk. Inclusion, relative monads give us a unified view on algebraic theories and monads. Left-hand extensions and free relative monads can be used for syntax, and right-hand extensions can be used for semantics of these technicals. And yeah.
So going all the way back in your talks where you talked about the free multi-categories.
Yeah.
So I can barely see the code, but just one frame that sort of starts with that. Sorry, all the way.
Yes.
So my question is, what do those objects have to do with relative monads?
Okay, so that was a bit of it's a good question. It's a bit of a kind of introduction to jumping between different categories and fixed points. So kind of the motivation was just to show that we can use index functors to model binders. Okay, run over. Yeah, we can use index functors to model binders, which is the standard way of doing it. And the point is that we actually go back to this category because these are signatures. You can see that we use them at the end. So these are the same thing, signatures, just been carried. So essentially, these are fixed points over these objects, and at the very end, we took the relative monad over these objects.
The relative monad over multigraph functor.
Yeah, the free relative monad over multigraphs or signatures. I use the two words interchangeably because the signature, multi-sort signature, yeah.
But they're not quite the same graphs and signatures, at least in terms of the types, really.
Yes. So this is encouraged because it goes from list to type, and then I turn it into a tuple because that allows the generalization easier. Yeah. Oh, there's no. No.
Can you show me code extension again?
Yes.
Yeah, sorry. It just you went through the code extremely quick.
Oh yes, sorry.
Yes.
Where are the extensions?
Yeah, 20 minutes for so you can.
Yeah.
Yes. It's very fast.
Take the extension of this talk.
Right. So here's the left-hand extension. So I did go through this part fast. I probably should have slowed down because if you haven't seen a CAN extension before and just saying, oh, you're taking left-hand extension might sound a bit abstract. So let me just try and explain it very intuitively. So we saw the coordinated type, which I explained as the free functor. So the kind extension, left hand extension, is very similar to a free functor, but instead of saying we have a functor from C to C, you say we have two functors, which K to type and K to type, and we create the functor between them. So it's kind of like, that's what it's doing. So it's saying we have this functor J, K to type, and this other functor K to type, and then we get back a functor type to type. So this essentially what allows us to form these pre-relative monads over fin, because I guess maybe I should have specified as well. Normally, if we have, where is it? Right. Normally, this would not be a monad because nav to type does not compose using functor composition. That would be a typo. Because to compose, if you have two functors nav to type, you can't smoosh it together. You need to be type to type or nav to nat. And so essentially what relative monads allow us to do is to make this into something that's like a monad by using kind extension. So we're kind of generalizing composition between functors to allow us to compose non-endofunctors. Yeah. So yeah, that's the type. Comment over A, an arrow from JA to B, and then some functor A that we'd like to get through.
J stands for variables and has to occur. And if you know
I guess I just usually see this convention called J, but I think of it as the context function. So this tells us what the shape of the context is. And then that is the.
So where do you use the long meter?
Yes. So we use it to refactor this guy. So we're using it implicitly here. So here essentially this thing is 1. So essentially we rewrite it, turning it into here. So here's 1 now. Again, let's do 1 through this very fast. So we use it twice. We use it here in our syntax, and we use it here in our semantics. We're saying that our algebras are. It's a generalization of manual algebras because you put coordinated here, as I hope I show next. Coordinated is a special case, so we recover extension systems by setting J equals ID. And then here's that's same thing as coordinated.
Someone asked in the chat. I didn't really see the right can extension at the last step.
Yeah.
Is it linked to the internal home of SOAS?
Interesting question. So to answer that, so right can extension, we're actually using it in the algebras. So
could you maybe zoom in if that's possible? Because the font's smaller here.
I see.
It's not showing up.
I can try.
Stream.
I guess it's no, but okay, so you can't see this.
Well, maybe try and like.
Right, so run here. We essentially for all of our type-chaining algebras, we're using run as the kind of the target. So we're essentially threading these traversals through run. I guess you can't really see it here because it's kind of implicit. Because I didn't define it as a data type. I defined it as just a definition as this thing. So it's just a particular shape of it's connected to. Okay, to explain this, it's kind of like a generalization of const t. So if this is m and this is m, then you get const t. And so const t is essentially the right-hand extension of a functor over itself. So I'm using this for like spectrums. But yeah, essentially we are using them in the algebras here and here. And similar with, well, type terms, we have, this is the kind of extension of the signatures. And okay, here we're using run when traversing over all type terms. It makes the type figure happy. If we don't use run, it's not going to accept the faults. And I think the fact it doesn't accept it is maybe one of the reasons people don't go for these shallow codes when they do this kind of theory. So it's quite good. I guess this is it's also interesting to me because this insight with right-hand extensions is originally by Neil, and the question at the start was originally posed by Connor. So this is like bringing the two sides of MSP together to combine. Yeah, is this? Do people know this? Is this folklore? Is this new? Like.
So then the second part of the question was the right-hand extension looks like the same type as the internal form of SOAS. And then they said, I guess they take the internal form of from F to G to be RAM var FG.
Yeah, I guess so. I guess it wouldn't surprise me if it doesn't overlap because semantically there's a big overlap between all the different ways of modeling binders. So yeah, I think that's not plausible to me, but it'll always be good to check and see if someone wants to make the link explicit, we could as well. Who was that from?
Hey you?
Yes, okay, and so for future work as well, first is extending this to kind of types, kind of types. That involves a bit of extra theory involving pseudomonads over bicategories, relative pseudomonads. Most know how to do it. You can actually capture quite a few different syntaxes using what we have now. So I didn't have time to write all the examples, but I can list them, which is we can do mutually defined terms. So two term judgments mutually defined. We can do mutual contexts. We can do weighted, aka graded stuff. So instead of a list, we could have this being a multiset with weights. So we can capture graded multi-categories, graded lambda calculi. And again, modality, that's usually two judgments mutually defined with multiple contexts. We can do that. One thing this doesn't explain is classical calculi, because in a classical calculus, you would have three term judgments, and you would have, usually they're called, let's say, terms, coterms, and cut rules. And term and coterm, you can think of them as monads, but cut rule has this really weird shape that I don't have a way to explain it using relative monads. It may be a profunctor, it may be a distributive law. There's some structure there that would explain why these two terms and coterms interact. And maybe someone knows this, I'd be interested in. And also another question is, how does this connect to tagless final? Because tagless final and church encodings, if you squint at them, they kind of look like they involve CAN extensions because church encoding is CPS transform. It's a CPS transform, and CPS transforms are, you think CPS transforms as special cases of right CAN extensions. So there might be a story there that can link this to tagless final. I have figured out, I think someone who knows tagless final and has some ideas.
Nothing else in the chat.
So, I mean, since this is proportion to solve a problem that was posed by EMSL, actually, who was the SL?
It was Connor, Bob.
Something for James James.
Yes. Oh, it's a solution. I mean, they also solve it, and I guess I haven't explicitly linked the two things, but I think there is a semantic.
What's the difference? Is it deep as a shadow headings or what?
Well, I guess descriptions. So using descriptions kind of explicitly describe the category. So I don't know what the formal, the actual category you're working in a paper, like which one it is. But another difference, I suppose, I don't know if you guys can do weighted stuff because this approach does weighted as a special case as well. and maybe we can do it using your work.
Or James Woods. uses the greatest.
Yes.
And the tricky part is that you, when you do substitutions and renamings, you have to make sure the weights add up.
Yeah.
I can't quite see how here, I can change lists, the
Yeah.
list of weights times time.
Yeah.
But you need to make sure, like here, even these rules,
Mhm.
you need to make sure the application, like the two contexts add up.
Yeah.
So
Yeah.
that's all the way through. And then when you do substitution, you need to make sure that when you're, as it were, pushing stuff in the right left,
Mhm.
that the terms you're substituting in split the right way.
Yeah. Yes, so this is a very good question. So right, this and I guess this is why, yeah. So how would I explain this? Yeah, currently, okay, so all of the examples here are using just kind of Cartesian context, so it's kind of very simple. If we're doing linear things and graded things, then we do need to do proper type splitting. And another example would be Phoenix, which also carry around this cover that shows that it's evenly distributed. So what I would say to that is carrying around these covers, kind of syntactically, we can do this. Semantically, I don't have a way to say what's happening. Like, what is the relationship between the cover or the splitting and the relative monad? I would like to have an explanation here and say, oh, it's a structure on the category of context that the relative monad is lifting to the lazy category of syntax. But yeah, I don't have the semantic explanation for how we connect the covers or the predicates.
One of the descriptions is that you're able to control the kind of signatures, make sure the substitution renaming always work.
Mm-hmm.
So you can never, the key thing is to never do anything global. All you ever do is add things to the tree.
Yeah.
And the same for the weights.
Mhm.
You never, to make sure substitution works, you have to make sure the only way you ever combine context weights
Mhm.
is linear.
Yeah.
Because that allows you to say that, because then the substitution is actually a linear transformation.
Yeah.
And you use the fact that you can push the linear transformation up to the because it says
Yeah.
so yeah, without having more constraints on the kinds of signatures,
Mhm.
it's difficult to get automatic
Yes.
substitution.
Yes. Yeah. So I suppose here we haven't gotten them for free. We've still got to write them.
Exactly. Yeah. So,
Yeah.
so if you come along with a different signature.
Yes. So it's a good question because
And here you can quite simply, which is bad, and since it says the context, it's only have that.
yes.
Substitution of that is probably basically
Yes. Yeah. So we don't have automatic derivative here. We can't define a single substitution for an entire structure, but the hope is that maybe didn't emphasize quite enough. I guess the idea is that because all of these things are given by can extensions, and if we had a bit more expressivity in language, we can actually define all these can extensions as a single can extension. Then the hope is that this kind of simplify the amount of proofs. Still kind of need to do some proofs in this case and some kind of sanity checks. But the idea is to kind of show the common thread between different type systems. And to some extent, I am hoping that you could build a deriving mechanism on top of this, which is again not going to be at this point not necessarily proofably correct, but potentially Haskell deriving could handle these examples, kind of give us for certain well understood contexts the responses. But yes, if we're doing graded stuff, we would kind of either have to carry around the proof that splits or end up with a lot of green slime here. So it's still how to do it nicely is still kind of a bit of a question, and also to talk about linear stuff as well, which would be an example. It's a bit subtle, but essentially we could replace. We would need to have, instead of fixing the context and varying the type, we will essentially be varying the two, both context and types. And so we have a list of contexts and a list of types when we compose terms. which again, we need to think about like a nice way to compose that looks like, because essentially it would be the generalization of splitting, but to a list. I don't know if there's a nice way to do that. Also, joint work with Jules is we're looking at substructural systems, and we're parameterizing them by generators in a category context. So the idea would be to have a parameter which says our category context has, say, swaps, or we can drop things, copy things, and just kind of recover a bunch of structural systems this way. We're also looking at effects in a category of contexts, which are effectful scopes, not to be confused with scoped effects.
So we can C++ call constructors and destructors, but the favorite.
Yeah, imagine if every time you copy a variable in context or drop it, an effect happens. Sounds gross, but actually it's in C++.
Okay, thanks, Zanzi again.